All right, awesome. Well, hi folks, welcome to CoCoFEST. My name's Henry, and today we are going to be looking at the initial booting up of the TRS-80 color computer, like from cold and dark, like using the aviation analogy of a jet that hasn't been turned on, from cold and dark to getting a cursor on the screen. This is not necessarily going to be a deep dive into a code. This is going to be just like, here's the process that has to be gone through in doing that. And again, my name's Henry. I run the YouTube channel, The Break Key, and this has been one of my major projects on my channel. Has been a custom OS ROM that pull out extended color basic, pull out color basic, pop in a ROM with this code in it, and it brings it up into a fourth-based environment. My first wild hair was, I would think it'd be interesting to write a fourth implementation. My second wild hair was, it'd be interesting if it actually booted the CoCo. Well, okay, so that's what I decided to do. Myself, I was, my earliest memories are of the Yukon Delta of Alaska. My dad was a gearhead. Mom wound up repurposing her career into computer science from education, because when we got back to the lower 48, Mom was overqualified for any job in the education field. So what did she choose? Computer science. This worked well for Dad. Being a gearhead, that means he gets to play with the toys that Mom needs when she's going for her degree. This was in around aboutish 1978, 1979 was when we came back to the lower 48. Mom got to a point where she needed to have a computer in the house so she could work on some of her assignments. And the one that actually flipped all the switches as far as what would be the most efficacious for her use case and what would be the most affordable for our family at the time turned out to be the TRS-80 color computer. This was my first computer. We got it in about 1981 when it first released. It was a D-board machine. With that, I learned my first language, BASIC, on the TRS-80 color computer. As we moved along, I became more and more interested in like playing around with this thing, and I was interested in some of the stuff that Mom was doing. I was interested in some of the stuff that the games were doing, and so I investigated machine language. So at about 10, I started teaching myself 6809 assembly language from the Leventhal book. I didn't really get to much that was functional at the time. I basically played around with the registers, and because we had an expansion on there on the CoCo, a monitor by the name of Wolfbug, which that Wolfbug came with a 64K and extended color basic in a package that Dad bought. I was able to examine what was going on in memory when I would run my little assembly language test programs. Worked pretty well. But I never really got farther than that, because truly, I've never been much of a fan of applications programming. I've never been much of a fan of like the higher level stuff. What I really found my interest in was in playing with gizmos, the gadgets, staying close to the metal. I really liked playing with hardware, putting things together, making things work, and assembly language was pretty darn close to it. Over the course of years, I also learned C, C++, Pascal, a smattering of other languages. I like to say that I'm fluent in over 6 million forms of communication, but I also like to say that once you've learned how to program, everything else is just syntax. And so I learned how to program. When in about, I want to say 2019-ish or something like that, maybe 2020, about 2019-ish, I came back to the CoCo because all of a sudden there's Dungeons of Dagerath. Ooh, I remember that one. And I came back to it, started playing around with it again, and now I can play with emulators. Now I can play with building assembly language programs. Now I can really start to dive into it. Now I have the internet. And the internet, especially with the Color Computer Archive, can get me absolutely anything that I could possibly need to know about how to get this computer to work and how to make things happen with it. How do I program it? What can I do with this processor? What can I do with this hardware? And that's when the wild hair started happening. So really quick, something that's not necessarily thought about by a lot of people is how much needs to be done just to get the computer to realize it's there. And I'm not talking about the processor. You apply a clock and you apply a clock and power to the processor, it'll start spinning its wheels looking for things. You know, it'll try to jump. In the case of the 6809, it'll try to jump to a vector located at FFFE. That's the reset vector. That's what it's going to do at first. Well, if there's nothing there at FFFE for it to read, it doesn't know where to jump. And even if it does have something there at FFFE, that's not an instruction, that's a destination, and the instruction had better be there or it's going to start spinning its wheels again. Program counter's going to sit, I don't know what exactly it's going to do. So the microprocessor by itself is, well, basically kind of useless. You have to have peripherals that are there with it. And with the color computer, your big parts to deal with are going to be the synchronous address multiplexer and the video display generator, the 6883 and the 6847 in turn. So when I first looked at this, my question was, well, if it sits at FFE0 or FFFE, ROM doesn't live there. Under normal circumstances, RAM doesn't live there. How do I get something to live there? Well, the real simple answer is, thanks to the synchronous address multiplexer, you don't. The synchronous address multiplexer listens to the addresses coming in, and then, based on the address that's coming into it, will set up a set of control signals. These control signals are 3 bits, three lines that come off the SAM, S0, S1, and S2. Those are fed into a 3 to 8 demultiplexer, and that demultiplexer is then used to send out, is that the one I'm looking for? To send out the control signals. So here's your S0, S1, and S2. If we look over here, you can see where you've got a control signal that comes over and hits the expansion ROM, and you've got a control signal that comes over and hits the standard ROM. This signal here at S equals 2 is the signal that enables the color basic ROM. That ROM space lives, when S equals 2, from A1000 to BFFF. What else is activated or otherwise enabled when it's sending out signal 2? Or what else does it need to send out signal 2? Look at this. Everything from FFE0 to FFFF, when the SAM sees that, it sends out the enable signal for S equals 2, which in turn enables the top of your initial ROM bank. So by having the SAM redirect those top 32 bytes of memory, those top 16 vector spaces, to the top of ROM memory, now I don't need to try and put something at FFE0. I don't have to try and put something at FFE, FFFF. I can put it at the top of my ROM space, and that will tell the computer where to go. By the same token, if I go into the CoCo and I do a peek of BFFF, I will receive exactly the same data and when I peek FFFF. Because again, the SAM sees that address of FFFF, activates the second signal line. So that's the first key. Where do I put it in ROM? I put it at the top of ROM, which I set down conveniently all the way at the bottom of this file. And let's see, BFFA is the error handler. That's the SWI. That's a blank space. And this would sit at BFFE and BFFF. So there's my vector to my start location. The SAM points to that. 6809 sees it on boot up, It says, okay, I need to go to wherever start is. Here we are. And bang. Now it knows where to go. Now the way Extended Color Basic does this is a little bit different. Extended Color Basic sets up a reset vector location in RAM. So ROM points to a jump instruction that ROM places in, ROM points to a jump instruction that is initialized by BASIC. So at the start of it, what am I needing to do? I need to set up my stack frame. I need to set up, like, where is my operating system going to look for the system stack? The system stack location is arguably the most important of your setups to do, because that tells the machine where it's going to store its returns, where it's going to have everything that it needs for all its branches, all its interrupts, everything like that gets stacked on that hardware stack. And of course, being a 6809, we can put that anywhere in memory. In this fourth implementation, I'm also using the user stack for my parameter stack, and I'm just setting a space for it. As long as we've got that stack available in memory, now the processor can start doing things as far as subroutine jumps, as far as interrupt calls, interrupt handling, and things of that nature. In my boot up sequence, I set the direct page pointer to the I/O page, FF1000, because that makes it convenient to do the next few things that need to be done. So, what have we got at first? Well, now the processor knows where to go. We've already had to figure out where do we put this vector location, and then now that we've got the vector location, we can actually start executing code, and that code has to set up the peripherals. The hardware itself is already set to determine where certain things go and where certain things will be, but to actually set up the operating parameters of the machine itself requires that you set up the operating parameters of, first and foremost, that synchronous address multiplexer. Without the synchronous address multiplexer, there is no computer for all intents and purposes. Without setting this up, the computer doesn't know where to look for things. The computer doesn't know how to get where it needs to go. It doesn't know what video mode it's in. The SAM and the VDG work together to determine what kind of video mode is being happened, and I'll get to that here in a minute. But the first thing that you need to set up is, how much memory do you have? Well, we can do a 64K static, we can do 64K dynamic, we can do 16K, we can do 4K. The SAM takes care of dynamic RAM refresh, so one of the first things I'll do is I'll tell it, well, I'm going to do a 0 map type, because the 0 map type is the one that has ROM and RAM in it. I'll make sure that's initialized. I'll make sure I set my memory size to something that makes sense. In this particular case, because I'm using a 64K machine, I'll set it to the 64K dynamic RAM setting. The MPU rate, I want to make sure that these are both set to 0 so that I've got a baseline. I have to do all of this explicitly in the code. I have to tell the SAM where the display offset is and what VDG mode to use. This is why I set this whole thing up here with loading X with FFC0, because of the way the SAM works. For you to set a bit, you store a value to an even address, or I'm sorry, yeah, that's a odd numbered address. For you to clear a bit, you send a signal to an even numbered address. Or do I have that backwards?
And it doesn't matter what the
It doesn't matter. All you have to do is assert the address bus with that address. And the SAM will see it and say, oh, you're asserting FFC0, so I'm going to clear V0. I'm going to clear register V0. So it could have been a load instead of a store in this particular case. And in each of these, that's what's happening here. Setting the display mode, setting the video memory offset. And because I'm using the X register, I can use the auto increment functions to be able to quickly move up a couple of spaces. So here we set basically clear the first bit, clear the second bit, clear the third bit, and by clearing all three of those bits, I've now set for SemiGraphics 4/text mode. This is just the SAM. Setting the video memory offset, I wanted to set that to 400. I wanted to set that to start at 400 hex. So that's what this sequence is doing. Page 1 set to 0 by definition, so that's a clear. Setting the CPU rate so that it's at slow size. Setting the memory size to 64K dynamic. And setting the map type to 0. All that has to happen before I can access a single byte of memory outside the SAM. All that has to happen before I can even think about putting video on the screen. Now, I will say in this I've taken a very simple approach. I haven't bothered to test memory to see what kind of memory I have available to me. I haven't gone through what I would want to do at first was maybe set it to the 4K mode and make sure that I've got 4K available. You know, test through that. Set it to the 16K mode, make sure I've got that available. And if I don't, fall back to the 4K mode. Set it to the 64K mode and make sure that I've got, well, in my case, at least 32K available. Possibly check for 64K to see what I've got, and set up the rest of my operating system to operate under those conditions. If you've got multiple memory maps, this entire section right here, well, this entire, where'd you go? CPU rate, memory size. This section right here is also going to have some logic. You're going to send a memory, you're going to poll the memory at that particular location and see if you get back what you expect. And if you don't, then you know you don't have it there. That would be another, I don't know, maybe 50 lines, maybe 40 lines of assembly code to get that loop and that structure going, just to test to see how much memory you have there. So I bypass the whole thing. I'm going to run this on a 64K machine. Boom, done. If I want to rebuild this to run on a 4K machine, which being a fourth implementation, it should very readily be able to do, I would need to have logic code here not only to detect that, where the memory is and where the memory ends, but I would also need to make in my system information, instead of setting my parameter stack to be equated to 8000 hex, I would want to have that be a system variable and have that set by the memory detection process. Okay. So at this point, the SAM's set up. It knows what kind of memory it's got available. We've set up the system variables that need to be set up in order for us to be able to know that we're not going outside of the area of memory that we have available to us. But we still don't have a single iota of sensible information coming out of the VDG. Because the VDG, all it knows is that, on the VDG, all it gets is the data that the SAM allows it to see. The VDG, if I can find it here, is fed its data directly from, directly by the addressing that the SAM does. The SAM is the heart of the system. If the 6809 is the brain, the SAM is the heart. The SAM doesn't care what the VDG thinks it's doing. The VDG, yeah, sure, it's got some address lines. You know, it's got more than enough address lines. But the only address lines that the SAM is listening to, as far as what address the VDG wants to listen to, is address bit 0. That's all the SAM needs. The SAM goes through a synchronization process with the VDG so that they get their clocks all put together. And they're talking at the same rate, they're talking together. That happens on the hardware level. That I don't have to worry about. Thank God I don't have to worry about that mess. What that means is that now the SAM is the one providing the data. I've told it is 400 hex. If I do nothing else, what the VDG will do with that setup now is just spit whatever garbage is in memory from 400 to 600 hex out onto the text screen. Maybe not even that, because I haven't told the VDG what video mode it needs to be in. I don't have that deterministically set yet. Could boot up in some random state thinking it's an RG6, in which case you're going to get graphics garbage. So the next thing, the error vector table I'm going to ignore for right now because that's part of the operating system. I'll worry about the variables later. But the next thing that really needs to be done to get it working is now I can't touch the VDG yet, believe it or not. I have to set up the interface adapters. So even before a single iota of video is set up, I'm having to clear out the PIA control registers. I'm having to set the PIA I/O directions. PIAs don't know what they're doing. They literally don't know anything about that. For them to do what the CoCo expects them to do, what the hardware the CoCo is designed around them to do, they have to be specifically told, this bit does this bit does this is an interrupt input, this is an output, this is what you're going to be doing as far as directions, this is what you're going to be doing as far as what you're listening, how you're sending, all that stuff has to be set up there. So the directions is a flag that's set on the PIAs. Let's see if I've got that loaded up. Do I? No, that's the 6847. That's going to be in memory map. There we go. So if we look at say this here, this is, where'd you go? This is the control register, one of the control registers for one of the PIAs, sitting at FF01. This control register controls the FF00 address area. If you clear bit 2, you've now set FF00 to be a data direction register rather than be an actual interface register. You're not listening to the interface at that point. You're now telling the PIA what direction are these things going. In the case of FF00, these are all going to be inputs, so I'll be setting them as input registers. Let's see if I can see that over here. Clear 00, load AFF, store A to 02. Yeah. Oh, you moved. There we go. Clear out the PIA control registers. We clear the control registers, and by clearing the control registers, that automatically makes makes 00 the directions. I clear 00. That turns all those bits on the A side, on the 00 side, to be input bits. And then by loading A and FF and storing that out in 02, that sets those direction registers. Now those are all output bits. And then I have to come back and reset bit 2 in the control registers so that I can now have those actually be input-output at FF00, FF02, FF20, FF22. Again, the PIAs are dumb. You got to tell them exactly what to do. And the clues for that come somewhat from this data sheet, but are from this information in the memory map. You know, what is it being used for? Do I need to set up this as an interrupt response? How am I setting it up for an interrupt response? But as far as like how to actually set these up, the 6847, or not 68, but the 6821 and 6822 PIA data sheets are what I had to refer to make sure that I'm doing it correctly. And that was a little faff of debugging to make sure that I had that done correctly. You know, in this particular implementation, I want to listen to vsync, but I want to ignore hsync. The other interrupt sources, the FERC interrupt sources didn't matter. So I wasn't worried about CTS, I wasn't worried about anything else. They didn't matter. But hsync and vsync did matter. Okay, so we've now got the PIA set up, the interrupt flags are cleared, and this was something that threw me for a loop when I was trying to figure out, well, why can't I sync things properly? It's because the interrupt flags, the way you clear the interrupt flags is by reading the input port, or reading the port. Not the control register, not directly resetting the flag bit, but by reading the port associated with the control register. If I've got an interrupt flag that shows up for FF01, then I have to do a read of FF00 to clear that flag. And that's what these are, clearing out all the interrupt flags for all of the for both of the PIAs. I mask fast interrupt and interrupt request because I don't want the processor to be, in this particular implementation, I don't want the processor to be responding to interrupts. My design decision here was that I want to work by using the sync signal, or by using the sync operation, SYNC. That operation still listens to the interrupt request line, or the FERC line, depending upon, I can't remember whether it does the FERC line or not. But by doing so, I'm not actually triggering an interrupt in the processor. Again, a design decision. Maybe I want to run interrupt, maybe I want to run interrupt driven. Maybe I want to do a little something different where I'm mapping out, you know, if I get an interrupt and I have this particular byte that's presented on the data bus when the interrupt comes in, then I can do a particular thing. That's actually something I do with the software interrupt later on down the line in dealing with error handling. And OS 9 also uses the software interrupt in much the same way. As far as the processor is concerned, the software interrupt is still an interrupt. It's just generated in software, but it does go through the full interrupt process. The external sources of interrupts can be masked. And that's what we're doing with FERC and ERC. How many of you here are familiar with the condition code register in the 6809? Okay, so we don't necessarily know what that is. I'll go into that real quick. So I need to pull up Leventhal. Actually, it might be in this one. Let's see. System description, memory map. No, I'm going to go grab Leventhal. Okay, so the register file of the 6809 consists of the A and B registers, which can be combined, as we know, to be a 16-bit register marked as D. Two index registers, 16 bits wide. Two stack registers, stack pointers, 16 bits wide. The program counter, 16 bits wide. the direct page register, 8 bits wide, and then your 8 bits of condition code. This is telling you the state of the processor as well as giving you the ability to control the processor. The condition code register is fully writable. That is to say, I can push CC, push SCC, to save the state in case I'm going to do something that's going to blow something up where I want to see that state later. I just did a calculation. I want to make sure that I keep the carry state from that calculation, but I need to do something else. So I can push SCC, do my other calculation that'll jack up my carry condition, then do a pulse CC, and now having done the pulse CC, that old carry condition is right back where it was. It's fully writable, so you can really screw some things up if you don't know what you're doing with it. But what I get here is I get carry, I get overflow, 0, negative, whether interrupts are enabled or not, and interrupts are enabled when this bit is 0. The half carry flag, which basically tells you when you have a 4-bit overflow, or not a 4-bit overflow, but a carry after 4 bits. The fast interrupt mask, active when this is 0, masked when it is 1, and the entire flag. The entire flag is what you use to tell whether you've done a fast interrupt request or just a regular interrupt request. Entire says, I've done an IRC, I've stacked everything. A lack of that flag says, I've done a FERC, there's only a few things that I've stacked. So masking off the fast interrupt request and the interrupt request was necessary in my case so that things that generate interrupts that I'm listening to don't interrupt the processor itself. I get to control how the processor responds to that interrupt in the regular code. So next, what needs to be done, I've set up the SAM, I've set up the PIAs, and once the PIAs are set up, now I can start talking to the VDG. Just a quick review. I had to figure out where to put not the starting instruction, but the vector for the starting instruction. Once I've got that figured out, that vector has to point to the start of code. Once I pointed to the start of code, that has to start setting up the synchronous address multiplexer, or ain't nothing going to work. Once I've got the synchronous address multiplexer set up, now I can start setting up the peripheral interface adapters that I can actually talk to the rest of the machine sensibly. I've already gone through something like easily 50 lines of code, setting that up. And if I do a more thorough and more robust job of doing my setup, possibly as many as 100. It's surprising how much you have to do just to get the computer into a state where it can do the things that we're used to it doing. And this is a simple 8-bit system. One of the simplest out there as far as the setup is concerned. So now I want to set up the VDG operation bits. Things start to get simpler. I say we'll send a 08 to address FF22, and 08 at address FF22 sets bit 3 of the VDG control output and clears bits 4, 5, 6, and 7. So bit 7 is the alpha/graphics flag. That clear tells me that I'm in alpha/semi-graphics. 6, 5, and 4 are my graphics modes. graphics modes 2, graphics modes 1, graphics mode 0. Those are the 3 bits that are used to tell you which P mode you're in. Clearing those out also says that I'm using the internal character generator. This is why sometimes if you've ever gone diving into this and tried to do P mode 6 type, or tried to do interesting things where you set up like semi-graphics 6. Semi-graphics 6 is set up by actually engaging bit 4 here, and you find that it just doesn't work because you wind up with these lines coming along. It's because it's also turned on the external character generator, and it's grabbing its external character data from text RAM. So with these 3 cleared out, I'm in semi-graphics 4. I'm in alphanumeric mode by having this cleared out. And I set this because for my implementation, I wanted the orange background. I wanted the orange and dark orange color set instead of the green and the dark green color set. I thought, hey, I'll be different with this, not because I don't appreciate our nuclear green glow, I do love it, but because I want this to be obvious at first glance. This is not extended color basic we're booting into. This is a completely different beast. I could very well have kept the character set, the character or the color set selection back at the green and dark green if I wanted to, by simply calling all of these to be 0. Now another thing you may notice is here on bit 2, there's a RAM size input for 4K or 16K. That is set up in hardware with a jumper on the original CoCo 1 boards to determine whether you've got a 4K installation or a 16K installation. So for ease, I could probably pull this and say, well, all right, I've got at least 16K if that comes up high. Once I set up the PIAs. But do I do that once I've set up the PIAs, or do I do that once I've set up the SAM, or when I set up the SAM, which is going to be the most efficacious? I don't know. This is only going to give me a distinction between 4K and 16K. It's not going to tell me whether I have 32K, 64K, or something else. And if I do my logic for detecting memory size when I set up the SAM, that's going to be just as robust. So I've got these set. Now the VDG knows that the data that's being fed to it by the SAM is actual character data. But that's not all. The way the SAM is set up in the VDG mode is very important here. So you've heard of the higher semi-graphics modes, right? The semi-graphics 12, semi-graphics 24. Have you heard of those? Okay. Who here is not familiar with those modes? Okay. So because the VDG is not directly asserting the address bus to get its data, the SAM's doing that for the VDG, and the data that the VDG receives is basically whatever the SAM says, this is your data. So the SAM has to be set up with reset dividers. And this one I know I've got a block diagram of in here somewhere. No, that's Leventhal. Oh yeah. That's not that. Here we go. Here's a block diagram. And what we have here are the 3 video mode lines. And they go to what's called an address multiplier and feed into the address counter for the VDG. Here's what this boils down to. The SAM will send, I think the multipliers are like 12 repeats. It'll have to send 12 repeats if you're in text mode. It'll send 6 repeats. You can bring that down to 3 repeats, 2 repeats, or like basically duplicating it once, or it only sends one time. You have to set the SAM to speak P mode 4, because if you don't set the SAM up to increment its address lookup every scan line, then P mode 4 won't give you 192 lines of resolution. If you set the VDG up to be in semi-graphics mode, and you set the SAM up for incrementing the addressing every scan line, what you get is semi-graphics 4 and alphanumerics available. Every scan line you can change what's in there. This is where semi-graphics 24 comes from. This is how we get like our Defender clones that run on that. This is how we get PACTAC. Instead of using a graphics mode, it's using the SAM to change out the data that the VDG is receiving every scan line, every other scan line, every third scan line, every sixth scan line. Not even respecting the graphics mode that the VDG is set in. This is all part of the consideration when you're bringing this machine up. You have to set the SAM so that it's sending, if you want to see text, you have to set the SAM so that it's repeating the same line of data, the same 32 bytes, 12 times. That's how many scan lines you get in text mode. And you have to set the VDG up to be in text mode. Okay. So now we have, after all this is done, we have a machine that has come up. Its heartbeat is there. The memory accessing is working. We've got our memory addresses set up where we're going to put our text information. We've got our interface adapters set up so that they're talking to the things that they need to talk to and the way that CoCo wants them to talk to them. And we've got our video subsystem set up so that it at least knows it's in text mode and is expecting to be submitting text mode information. But we haven't yet cleared the screen. So at this point, all we've got on the screen is whatever garbage is in memory at the address we've pointed to. Nothing sensible is there. Depending upon how your machine boots up, you might see the bars and ats. Okay, and fun fact: those bars and ats are alternating FF00, FF00. The at sign in what we consider inverse video is 0, and that FF, because of the way that the VDG is wired up, that high let's see, I think it's the high, yeah, it's the high bit, that bit 7 swaps it out into semi-graphics mode. And I can show you that on the schematic. (6809), 6803, that's the PIA, that's the 6847. If we look at our alpha semi-graphics mode, which is a separate switch on the VDG, that's tied to bit 7. The inverse mode is tied to bit 6. These 6 bits down here are what actually are providing you the information of like what character you're displaying or which semi-graphics character you're displaying. And these 2 bits are doing nothing more than act as switches. So theoretically speaking, if we were to rewire this and add in a, what's the word I'm looking for? Add in like the color byte or something like that. We could easily say, all right, you're going to be in alphabetic mode. Inverse is going to be on and off. There's a couple of other things here that can be set up per character cell. It polls per character, and these 2 are one of those. We could have an external. We could take the internal external signal, pull that off, and set it up to use a different ROM. As a matter of fact, some of you may have heard of the lower kit, and that's what the lower kit basically does. It frees up that line from the physical reins of the CoCo itself, and allows you to set it up to use an external character generator ROM. But all that said, now we need to clear the screen. But now with everything set up, things are going to start getting a little easier. Because now the computer's in a sensible state. Now I can just spit things into memory and it'll show up on the screen. I don't have to worry about that because I've gone through the 50 to 100 lines of code that I need to simply get it off the ground. Oh, you keep moving on me, you silly, silly thing. So let's see. Very simple. Load D with 2020. Load X with where my screen top is. Start storing that and incrementing. This saves about a cycle or so by using D instead of using A and B. I mean, I could just as simply go through and stack last, but I decided to do it this way because I didn't want to mess up my stack registers. And then you just keep running that until you get to the bottom of screen memory. Bob's your uncle. You're done. And why 2020? Because it turns out that hex 20 is, for what I was implementing, not only is it the ASCII character code for a space, but it's the dark color of space. It's not the light color. Okay, great. I've cleared the screen. Now we get to pull the keyboard. We don't have the luxury of having a keyboard that hands us at a particular port, at a particular I/O space in memory, an ASCII character. Oh no. The CPU is doing all the heavy lifting with this. It is doing the keyboard decoding. No, nothing's offloaded here. You know, spared no expense. So this is where we run into another problem. Is those key switches don't have those nice little diodes. Not only do they not have those nice little diodes that make it so that ghosting doesn't happen, but they also don't have any type of debouncing whatsoever. So the signal coming in is going to be noisy. If you just pull the keyboard at some point, you may not get the key that you're expecting because it'll rise, it'll fall, you may get a double tap or something like that. You have to do debouncing. Well, there's multiple ways you can do your debouncing, and well, they're not being implemented in hardware, so we've got to implement them in software. One of the ways you can do debouncing is by polling the keyboard like 2 or 3 times in a row with a little bit of delay between each poll, and make sure that you're getting the same signal in. If you poll, like, say, I think it's Extended Color Basic does it twice. Poll, delay, poll. And if both polls are not the same, it rejects the input. I decided to go simpler. I just said, every new frame, we'll wait till the beginning of the frame, and by the time we get to the beginning of the frame, the debounce should be taken care of. And I'm not going to poll again until the next frame comes around. So I'm automatically adding a 17 millisecond delay, allowing for, like, if it's going to have problems with bounce, you're not going to have a problem with bounce that's going to last 17 milliseconds. It's going to be on the order of like 1 or 2 milliseconds before the make break is done, unless your keyboard's really wonky, in which case you might want to replace your keyboard. But so by doing this poll at most once every 17 milliseconds, I can just do a simple one-off poll and not have to worry about doing it multiple times. So here I hit sync, and here again I have to read in FF00 and FF02 to clear the interrupt flags. If I don't clear those interrupt flags, then the PIA is just going to keep signaling the interrupt. It's going to keep that line active, and I'm going to wind up coming right back to it, and I'll wind up just in a spin loop that's going to go just lock everything up. So I have to clear those interrupt flags. I begin the keyboard poll. And this is a ridiculous mess of getting the, getting the keystrokes in, getting the raw data in for it. Then processing that raw data so that I can know which keys have been released, because I need that information as well. Not only what's actually down right now, but from the last one I can find out which ones were released. I can run my column checks to see which column. I can run my individual column checks and see which rows are coming off. The basic idea being this: you send a signal to a column, and this signal, because everything in the in the CoCo seems to be active low, that's going to be setting a particular column to 0. And when you set that column to 0, let me bring the matrix up. Where is it? When you set that column to 0, then when a key is depressed, that particular row will run active. So now, column by column, I strobe each column with an active signal and pull in the signals for the keys that are depressed in that particular column. Once I've got that in, I can take those signals and I can say, all right, well, I got a signal here that is a press at H. So I need to prepare to put an H on the screen or send it to the output buffer, whichever one I'm going to be doing. Well, at the same time, maybe I've got an X. I'll grab that. But I make a priority in my implementation. The first row it checks is row 7. 0, 1, 2, 3, 4. I'll call it row 6. The first one it checks is row 6, which is where enter, clear, break, and shift are. If shift is down, that changes the state of how I'm going to be dealing with the keyboard. In the CoCo 3, you've also got your Alt and Control keys there, and that would similarly change the state of what's going on in the keyboard. Enter, clear, and break have special meanings to the system. Enter not only concludes a line, but says, process the line that you received, let's get this going. So that kicks off some things, that's priority. Clear, I'll clear that out, clear, obviously that's going to clear the screen. And break is going to end whatever it's in the middle of, or at least it's supposed to end what's in the middle of it. Those are the first things I process as soon as I can get my hot little hands on them. Which one of these, and they're the most important. They kick off their own things. And then after that, I can go through and check my other rows and see what I need to put on the screen. And this whole process starts up here. I've got them named like main loop, and main loop runs all the way down here. That's at 256, and that is 180. So that's about 70 or 80, 85 lines of code. 90. I didn't do the math right, but lines of assembly just to get the polling done, and that doesn't include the lines for the subroutines that are called when it runs in these conditions. Okay, we start the keyboard poll, we clear the shift flag. Initial setup to poll column 7, like I was saying, and then we go through the poll loop, send the poll, grab the value. We're going to be playing around with it. Have we passed? If we have passed column 7, then we skip the shift key check. Otherwise, we check to see if we've got a shift key, and I set the shift key, just like I was talking about before. Start processing the releases. Do the column checks. Are we in column 0, 1, or 2? We can skip, enter, clear, or break. Do we have either of those? We can keep going. Otherwise, we go to a subroutine that processes enter, clear, break. Do we have a character to handle? It'll tell you. It would tell me that. If we don't, we can just keep on going to the next one. If we have a character to handle, we need to calculate the column number. Do this and this all this mathy stuff. Basically, is like, all right, which character is it? And then we continue with the row loop. And all I'm doing with that is I'm running a rotate through carry to make sure that that I get that 0 in there, and that 0 sits on any particular one of those. Once the carry clears, then I know I'm done with that polling of the keyboard. So, all right, great. I've got keyboard polling, and it's listening to things. There are other things that are going on with that. So what about the cursor? Well, I wanted to have something that was kind of cute. And you've probably already seen probably already seen my display. Oh, it doesn't like that. Probably because I need to... Oh, I know what happened. Oh, it's not happy. Oh, well, I can't, for whatever reason, it's not coming up. But you've probably already seen the display. And what I did was a little rotating cursor that changes through the colors. And that's actually got its own code. All right, there it is, show cursor. I have to get the current position of the cursor because that's something that I got to keep track of throughout this entire thing. Where is it in the input buffer? And I have to wait 4 frames in order for the cursor to be visible as being rotating. I have to wait 4 frames, 4/60th of a second, about like 54 milliseconds or something like that, before I can update the cursor shape. And then I grab the, I will grab the current cursor character at the current cursor. If it's a blank, I can just if it's a blank, then I need to initialize the cursor. And I go through all this code right here. That subroutine, just to make a little thing spin. And to get there, I had to go through all that code that made the VDG speak text mode, that made the SAM speak to the VDG, SAM feed the VDG the right data, that made the PIAs so that they could talk to the VDG and tell the VDG what to do, and that even just told the computer, hey, you're a computer today, not just a piece of silicon spinning your wheels looking for something at address FFFE. This process from raw cloth took me easily, I'd say 16 to 24 hours of work. if not more, just figuring out why things weren't working. This sequence of just getting to a point where I'm entering in data and having it show up on the screen, entering keys and having it show up on the screen. I think it took me about 3 videos, maybe 4 videos, before, I think it was 3 videos, to get to the point where I was actually showing stuff on the screen when I typed it on there. And it was a huge, huge success. The computer didn't do anything but show the characters that I was typing and show a pretty little cursor on the screen. And it took that long and that much to get it there. Any questions?
Real fast.
What's that?
A lot of text, right?
What's that?
Takes a lot of text to happen real fast. As compared to basic, it goes back and forth.
Well, I looked at basic to see how, I looked at the basic, the Unraveled series to see how it was being handled, so I could take that and adapt it. Some of that is so spaghettied up, though, I just couldn't follow it, so I had to come at it from raw cloth. You know, so this isn't necessarily faster than basic. It might be leaner than basic simply because I've not done some of the checking that basic does, or I've done the checking in a different way. But you know, basic does things in a different way that, to a certain extent, could be considered more robust, but to a certain extent could also be considered legacy, because what Bill Gates was doing with Microsoft Basic was, you know, he's got this code base. I just want to port it, he says. I just want to get it working. Yeah. Yep. Yep, it rotates through colors and it rotates through shapes. So like when I've got the fourth machine booted up over on my display, you can look at it and you can see it does this little rotation. And it does the rotation, it goes through the colors. I wanted the multicolor cursor like we've got with the Coco Extended Color Basic, but again, I wanted something that was definitely going to show you're not an Extended Color Basic, and I thought that was nifty. Nifty little animation to have. Any other questions?
One thing is still not clear to me. Does that mean that after it's read your key press and decided where the cursor belongs, is it leaving you in graphics mode then?
Okay, so after it's read the text, after it's read it, put it on screen, and going back to the cursor, is it leaving it in graphics mode? No, because I'm in alpha semi-graphics mode. And remember that semi-graphics mode, even though that's a separate pin on the VDG. Oh, it's in the, okay. Here we go. Even though like alpha and semi-graphics is a separate pin on the VDG, that's tied to bit 7. So and is that correct? I think so. Yeah, there we go. Come on, I want you bigger. There we go. All right, so like this is something that you might have seen. If I poke, say 7F. Come on. To address 400. That gives me a question mark. If I poke 81, I would poke 80, but 80, but the 8 series is green. But if I poke 81 in there, now I get a semi-graphics character. So all of the semi-graphics things, like when you do set and reset in the good old days, let's see. And that was, I think that's 32. And then I'll go with 8 on this, on 7 on this one. Does anybody remember if I need parentheses for set? Watch this not work. Oh, it does. Okay, so now it's got a function called arn30. But so when you're doing these sets and resets, all it's doing is it's taking that information. Oh, I see what I did wrong. When all it's doing is it's taking this information of the set and reset, and BASIC is translating that to the graphics characters that need to be placed. You'll notice sometimes when a new set happens that the color of the entire block changes. Within a given character cell, if you're in alpha semi-graphics mode, within a given character cell, you can only have one color and black. So I don't have to switch back from graphics mode to text mode for the cursor display, because the cursor is in alpha semi-graphics mode. It's using character addresses that are above 80 hex, at or above 80 hex. Does that make sense? Does that answer your question?
Yes, but I haven't seen your display, so I don't know what it looks like.
Oh, okay, yeah. I would show you here, but demo gods are giving me grief. Yeah, but if you get a chance to see my display, you'll see that little cursor going. I'm here tomorrow too, so. Any other questions? All right, awesome. Well, thank you much for showing up. Appreciate it.